Hi everyone. So in this video, we're going to talk about your computer. We're going to look at all of the different parts that make up your computer and see what the function of each one is when we talk about a program actually running. We're going to look at what happens when a program gets loaded into memory when you execute it, and talk a little bit about the role of an operating system in being this balancer that ensures all your programs get a fair share of your hardware's time. If you've ever opened up your computer before to replace or upgrade a component, some of this might look a little bit familiar, but our goal in this video is just to make sure that you all have a common language to talk about hardware and software, so that when we say, oh, our program's going to go and open up a file, you have a little bit of an idea of what's happening actually in the physical world, what electricity is running to where on your computer, and so that we're prepared for some other information that we pick up as we start learning to program. So I want to start off by talking about just a couple of the major hardware components that we've got. And I'm specifically going to target just these few here. There are definitely others, and there are other ways we could break it down. But the thing I want to start with is talking about a processor. So the CPU, or the processor, the central processing unit, is really the thing that people talk about when they say, oh, I'm modeling a computer, I'm making a computer, this thing is a computer. As the name would suggest, this is the thing that does the processing. What a CPU really is, when we come down to it, is a bunch of wires that are organized into a collection of circuits. And each one of these circuits is a special way to run electricity, so that we take some inputs, some current running along one side, it goes through this jumbled pattern, and then out the other side, we get some outputs. Each one of these circuits is typically used to perform some type of calculation or comparison. We can talk about a greater than circuit or an adder circuit, but all of them work by feeding in electricity on one side to represent data in ones and zeros, because remember, all information, whether it's text, whether it's numbers, we can turn it into ones and zeros, or on our wires, yes, there's electricity, or no, there's not electricity. And then out the other side of these circuits, we get some other resulting pattern that is the result of adding those numbers together, or comparing them to see which is greater, or whatever of the hundreds of other little logic units are implemented on your particular CPU. So the important thing to note about this CPU is that it's got very, very limited space, registers to temporarily store something, like the numbers it's in the middle of adding together. But generally, the CPU's job is just to combine things, to mash them together, do the comparison, do whatever other operations it knows how to do. And then as soon as that electricity flows out of the output, it's forgotten about whatever that thing is. It doesn't hold on to things in the long term, but it is very, very good at computing and giving you some result. So a great analogy I've actually had some students tell me in the past for the CPU is little models of computation in video games. If you've ever played Minecraft, a lot of my students play Minecraft apparently. There's the redstone wiring that you do. When you do that, what you're modeling is actually this CPU, this central component of your computer. So that is the single most important part, but it's by far not the only part on our computer. So as we talked about, one of the big weaknesses of the CPU is that it can't store anything longer than fractions of a second, or at least it can store very, very, very few things. If a program does need to store things for a long time, then typically the way that we do that is by moving that data into running memory. So running memory is just a cache of millions of little cell circuits that each have some way to encode a 1 or a 0 with a bit of electricity. So the CPU had a bunch of these different circuits for all different operations. Running memory, what we often call RAM or DRAM, just has a lot of copies of one circuit that knows how to either keep a 1 held in place or keep a 0 held in place. Yes, there is electricity on it, or no, there is no electricity on it. And by feeding in electricity into these circuits, filling up the ones that should be 1, letting empty out the ones that should be 0, we can store these patterns of 1s and 0s as long as we need to. And the neat thing about our DRAM is that each one of these cells is addressable. We don't just have 1s and 0s in cells, we have the location of each one of those. We can say, hey, jump to the 10,264th one of these and grab the next 8 because that's the integer number that I want to pull into my program. That name for this running memory, DRAM, it stands for Dynamic Random Access Memory. And that random access part refers to the fact that these cells are actually pretty cleverly organized, so that no matter which one you want, it takes the computer the same amount of time to run out, grab that data, and pull it back into the CPU to do whatever you're doing with it. However, this does come at a cost. RAM is also volatile. What that means is that in order for your stick of RAM in your computer to hold on to whatever numbers you're storing, it needs a constant feed of electricity to sort of refill those electron buckets in those cells to keep the 1s as 1s. If your computer turns off, everything levels out and drops down to 0, and everything in RAM is lost. So RAM gives us a place to store things, and it's very quick to access, but it's still not permanent. If we want to permanently store something, then we need some more physical way to store this data, and the piece of hardware we use for that is our persistent storage. And of all of these different parts that I'm showing you, persistent storage has by far undergone the most number of complete transformations over the life of computing. We've stored it on everything from large rolls of magnetic tape to disk platters to CDs to flash drives. They're even now looking at ways we can store on crystal, actually encoding right into special leaded glass and how densely we can pack information on that. But whatever specific technology we're using, the actual mechanics of persistent storage tend to be very similar. Much like our running memory, persistent storage has some way to represent a cell, some way to represent a 1 or a 0. And the thing that's different about persistent storage is when we want to encode that 1 or that 0, we make some physical change to the storage medium. So as an example, on an optical CD, you know those kind of donut-shaped glass things you could hold in your hand? They looked like a rainbow on one side. The way those actually worked is that a laser and a little lens would run up and down, and they would reflect light off the CD. And when you wrote the CD, you'd actually be burning in little divots on that glass surface, so small you couldn't even see them with your eye. But then when you go to read the CD, the light reflects differently off of those little dips. And so the lens knows, oh, I am sitting above a 0 or I am sitting above a 1. And the neat thing about this is, unlike our RAM, we've created a change in the physical world. Even if the computer turns off, that CD still works the same. And that same principle applies with old hard disk platters like this drive shown right here. We'd be magnetizing small little bits of metal, polarizing it to face north or south. And from that, we'd know, hey, this is permanently magnetized this way, so this means this cell of data is a 1 or a 0. So this is great because it finally gives us a way to store information longer than the life of a program. But there is a trade-off. Because we are impacting the physical world, typically this takes a little bit longer, it's a little bit slower. With old things like hard disk platters, like the one shown here, you don't even have access to all of the memory at once. The ARM is sitting above one particular spot on the drive, and the drive has to actually spin into place if you want to check a different address. And so persistent storage tends to be orders of magnitude slower than our RAM was. And so what this means is typically when we want to read from it, we do so in large buffered chunks. We queue up, hey, I want to read this, get it to me when you can, and it takes the computer a lot longer to do that than it does to just read from a slot in RAM. Some of these mediums are not random access, like we talked about that spinning platter. So it might even be necessary to periodically defragment that device to move all of the related information close to each other so that we can access it efficiently. And all of these are extra problems with persistent storage that we have come a long way in addressing. New memory like flash memory actually works much more closely to RAM than things like disk platters or CDs, but it's still not going to be nearly as fast. So we have these two different places that we store things. RAM for stuff that we're going to be using right away, and persistent storage for things that we want to store permanently, but we're probably not going to be constantly updating anymore. So those three components there, the processor, the RAM, and the storage, those are the three most important bits of your computer. They are the parts that let any average program run. But they're not the only things that we need. Most importantly, we need some way for these three pieces to talk to each other and to talk to every other device that you hook up to your computer. So in order to do that, we have one more device that is crucially important on your personal computer, and that is the motherboard. So the motherboard, despite its name, is not mother to all these things. It is sort of just like the highway that all of these things use to talk to each other. It's one very large board with a bunch of sockets and connectors that let it serve as an interface for all your other parts, sort of like an information highway. So when you get your CPU, the CPU plugs into the motherboard in a socket. Usually it's all of these little pins pointing up, and you line it up very carefully, pray that you're not about to burn hundreds of dollars because you misaligned them, bend a pin. But then every other piece, your RAM sticks come right next to that CPU. Normally they're very close together because remember, the goal of RAM is to be fast. So we don't want it to have to travel a long way whenever it reads information, sends electricity. But we've also got room for many other different parts. We've got expansion card slots that we'll talk about in a minute. We've got USB headers that let you attach a cable out to a USB port. We've got fan headers and hard drive slots, whether they're SATA or M2 or some other connector. But it's all of these different pins and plugs on one board. And then the motherboard's job is just to figure out how to let all of these different pieces talk to each other in a fairly efficient way. In addition to this, it also does manage power, so it will run electricity to all of the ones that don't require an excessive amount of power. If you've got something like a discrete graphics card, that needs so much power nowadays that usually there's this extra external cable you also plug in. But the motherboard does do a lot of the power management as well to feed all of the electricity to all of these different components. One of the neat things about the motherboard is over time, things that used to slot into these extra slots down here, things that were expansion cards, have come to be so cheap to make, so universal, that there's no difference in quality anymore, that now most motherboard manufacturers just print them right on this board. As an example, a sound card, when I started using computers decades ago, was an actual external thing that you bought. You bought a sound card, which was a little device that plugged down into one of these slots down here, and it had ports out the back for speakers, for a microphone, whatever depended on the sound card you got. And you actually, if you didn't have that, your computer could not make sound. Nowadays, the processing power we need to do that is so small relative to everything else the computer is doing that sound cards are typically, unless you're an audiophile, you're doing audio in some professional setting, you probably just use the one right on your motherboard. Same thing with network adapters, things that let you talk to the internet. Used to be, you went and bought a separate device, plugged it into one of these slots, and that was how you could actually talk over Ethernet or over Wi-Fi. But now many, not all, but many motherboards have onboard cards for all of this. So that's the other thing that the motherboard does do. But this does bring up that expansion cards do still exist. People use their computers in a lot of different ways. And so to account for this, motherboards often include a wide range of semi-universal ports that let you plug and play whatever other devices you need. So some of these standards, like the Universal Serial Bus, or USB, is a little component that just has a header on the motherboard, and you run a cable out to a case or something else, and then you can hot plug things in and out on your computer as you're using it. Others, such as PCIe lanes like these pictured here, have a more direct access to hardware so that the things plugged in there run a little bit more efficiently, a little bit faster, in exchange for that loss of portability. So these PCIe lanes are often used for things like a GPU, a discrete graphics processing unit. And in these slots, we are able to address the little logic units, the gates on these GPUs, the same way that the CPU would access its other components. So the CPU can sort of hand off data to the things in these slots, wait, receive a result, in the same way that it would read to or write to or read from any other input or output. And this makes computers very modular, and it makes it very easy to add new features onto an existing machine. So this is our introduction to computer hardware. As I said, the main goal of that was so that you can start to understand what people mean when they say the CPU or a GPU or RAM, so that as we're programming, you have a better idea of where your information is actually flowing in the real world and how it passes from device to device. Now, I want to shift gears a moment and talk about what does this mean for an actual running program. So let's say I have Firefox.exe on my computer, and I double click it, and now it's running. What is actually happening on these hardware components? So what happens when we run a program is, before that program runs, it's stored in our persistent storage. All of the instructions that make up how to be Firefox are written one after the next and translated down into a bunch of ones and zeros that say, hey, take this data, put it on that circuit in the CPU. Take this data that you get out of it, store it in this place in RAM, and then 3 seconds later, pull it out, put it in that circuit. All of those instructions just live as ones and zeros on your storage device. When you double click the program or tell it to run on the command line, your operating system says, okay, let me take these instructions and pull them all up into the stick of RAM. Because I'm going to be using them, let me load this into the computer's running memory so that it's quick to access it, so there's not a big delay as I use the program. And then your CPU starts reading those instructions one at a time, loading them into its little registers for whatever it's actively doing right now. And then it keeps count of, I'm currently on instruction number 3000. Now I'm on 3001, 3002. And it goes line by line through that program, reading it from RAM into the CPU, doing whatever it needs to do for that step, and then continuing on. And in your program, like when the program was written, typically, as we discussed in our lecture on the history of programming, we tend to like to write these programs in a human readable way. So what that means is, in order for the CPU to understand what we're doing and what the program is supposed to actually instruct on the hardware, there needs to be a translation that occurs. And there are sort of two ways that we can do this translation. Either we can say, okay, I am done writing my program. Computer, go and translate it for this hardware right here. That's what's called compiling a program. And anytime you get a binary executable file, a .exe on Windows or a .bin in some operating systems, anytime you've got that double clickable program thing that just runs by itself, typically that's a compiled program that was compiled for your specific hardware, your specific operating system. The other alternative is, instead of translating your code and having that be what runs on the CPU, you can run a program that knows how to do that translation in real time, what's called an interpreter. So interpreted languages are always run by running their runtime executable and then feeding that the location of your program. So as an example, Python is interpreted. And so when we run a Python program, the first thing that gets loaded into RAM is actually not what you wrote. It's python.exe gets loaded up, the thing that's already been translated that you install before you can ever write a Python program. And then you tell Python.exe, go load myscript.py, and that program that was already written knows how to read in your instructions and then translate them into whatever it is the CPU needs to do. And so this has a benefit in that it is a little bit more portable because it is one level up from working on the hardware. So the instructions that we can express are a little bit more complex. The drawback, however, is that translation does take some time. So interpreted languages do tend to be a little bit slower than compiled languages if you're doing the same instructions. The hope is that because you have better, more complex instructions, you can still do it more efficiently, come up with a better way to say it, say whatever task you're trying to perform. But No matter what, when your computer runs a program, somehow it's taking some compiled executable, running that, and then translating instructions into things that actually run on the CPU. So that is our nice starter model of how to run a program. However, there's sort of a gap here still between the program that is running this way and the hardware that is actually the physical electricity. Like, what is it that's allowing us to double click that program? And that thing that sits in the middle, that is what is actually referred to by this term operating system. So an operating system is sort of like the software version of our motherboard. Just like how the motherboard is acting as a bridge that facilitates communication between all your hardware, the operating system is a bridge between all of your running programs and the hardware that those programs need. So there are several different popular operating systems. Most people end up using Windows or Apple, but there is also Linux, the mobile operating systems, iOS and Android, and there are even several other specialty flavors out there of operating systems, things like BSD and Solaris, that are all each specialized to some computing environment. But what all of these operating systems have in common is that they implement a few crucial responsibilities that tell the hardware sort of how to balance all of the different things that they need to do. So every operating system's biggest job is to load drivers. And drivers are just small little hard software components that describe how to translate instructions for a particular piece of hardware. So your CPU will have a driver that says, hey, this CPU, this 23rd wire from the left, that one is the one that goes to the adder. So if you want to do adding, the way that you translate an add instruction in bytecode to my particular thing is send electricity on that 23rd wire. They say, oh, well, you know, this device operates at this frequency. So if I'm sending you a bunch of data in sequence, this is how long you have to wait for each 1 or 0 to come down the wire. They say everything that's required to use a piece of hardware, what capabilities it supports, and how it maps to physical running electricity and circuits. So that is the most important thing an operating system has, is some kernel drivers that describe how to actually use the machine that the operating system is loaded on. But equally important to that is that an operating system also acts as sort of the mediator between programs. Most people, when they use their computer, aren't just running one single program. They run several at once. They might have a browser open and a chat program, maybe a text editor for taking notes. Every operating system, or at least every multi-process operating system like Windows or Apple or Linux, has a scheduler. And the scheduler ensures that every program gets a fair share of time with the CPU and the RAM and the other hardware components. Scheduling can take many different forms, but often it comes down to rapidly swapping in and out which program is the active program. So your operating system keeps this record of everything that's running, and even though when you use your computer, it feels like everything's happening at the same time, what is actually happening is your first program gets 1/10,000th of a second. Then the next program gets 1/10,000th of a second. Then the next program, then the next program. And once they've all got a turn, it jumps back to the first one, and round it goes ensuring that nothing ever gets completely starved out and freezes entirely. As part of this, the operating system does also monitor if a program is misbehaved. It says, oh, well, this one isn't really giving up its turn. Looks like it might actually be frozen, and it manages handling that, whether it's culling it or alerting you, the user. Another big piece of this is that the operating system needs some type of security layer to ensure that program A can't read from the RAM of program B. If you could do that, then if you ran my program on your computer and then typed something, a password, let's say, into another window, I would be able to read your password, even though my program has nothing to do with what you're doing in your browser. So the operating system typically has some way to constrain and restrict access to the hardware. And then it implements some system calls that allow programs to make requests when they want to use that hardware or when they want to do some other privileged action, something that's normally protected. And so this operating system sits in the middle. And the neat thing about this is it kind of acts to hide what is going on in the hardware. So most of the time when we write programs, we don't even have to think about, oh, well, I have to send this to RAM and that to persistent storage and this to this logic gate on my CPU. Because those system calls give us a unique standardized interface that works on every computer, no matter what hardware it runs, we as the programmer get to spend our time up in software, in whatever commands our programming language gives us. And that program will still work the same on every computer that runs it, even if the hardware doing the processing is completely different. So this is just a really basic introduction, a high-level overview that we did today of the parts of your computer and the system that actually runs your program. We talked about a couple different pieces of our computer, different running components like the processor, the RAM, the storage, and the motherboard. We talked about how programs actually get loaded in when you run them, from storage to RAM, and then executing on the CPU one instruction at a time. And then we talked about how the operating system acts as the mediator between all your running programs, sharing access to the hardware and securing access from one program's data to another. So hopefully this gives you some insight into what happens when you run your programs. From here, we are going to get started talking about file systems and then variables, actual data storage inside programs you've written yourself. So look forward to that, and I will catch you all in the next video.